Algebra 2, Chapter 13, Section 1, Rational Functions. A rational function is a function that is the ratio of two polynomial functions. Here the word rational has to do with ratio, has nothing to do with how well you can think about these functions. It just means the function is the ratio of two polynomial functions. So p of x is a polynomial and q of x is a polynomial. Write each expression as the ratio of two polynomials. In other words, put each of these expressions into the form of a rational function. So in order to do this, we need to multiply the 6 by x squared over x squared to get 6x squared over x squared, which then gives us 6x squared plus 1 all over x squared. And now we have this written as a ratio. Part B, we have x squared plus 2 over x minus 3 plus 2. So we need to multiply the 2 by x minus 3 over x minus 3 in order to do the addition in the numerator, which will give us x squared plus 2 times x minus 3, which is 2x minus 6. 2 times x is 6, 2 times minus 3 is minus 6. All of that will go over x minus 3, which would equal x squared plus 2x minus 4 when we combine the 2 into negative 6 over x minus 3. Part C, we have this complex fraction. In order to deal with this fraction, we should multiply by the denominator of the inside fraction by itself in order to cancel that inside fraction out. So we multiply by x over x. In so doing, we'll have x, where the 1 was, plus x over x, which is 1, over, and here we have x times x is x squared, minus x over x is minus 1. So x plus 1 over x squared minus 1. And if we remember that x squared minus 1 is a difference of squares, we have x minus 1, x plus 1. Now we have a common factor in the numerator and the denominator, but canceling it would not make an equivalent rational function, so let's leave that alone. D. Well, we can just write this polynomial over 1. 1 is a special kind of polynomial, and that would make it a rational function. So that's all we have to do for D. Let f of t be 50 plus 1t represent the population in millions of a country in year t, and let g of t equal 200 plus 0.05t plus 0.03t squared represent the gross domestic product, GDP, in billions of dollars. The per capita GDP is the GDP divided by the population. A. Demonstrate that h of t is a rational function. So h of t would be the per capita GDP, which is, I think, what is implied here. Okay, so the per capita GDP should say the per capita GDP h of t is the GDP divided by the population. So in order to show that, we show that h of t is the population. Let's see, so it's per capita is the GDP, which is g of t, divided by the number of people, which is f of t. And of course, then we can write the rules for each of these functions. 200 plus 0.05t plus 0.03t squared over 50 plus 0.1t. B. Evaluate h of 0 and h of 20. What does this tell you about the country's economy? So h of 0 would be when the year is year 0, whatever that happens to mean. And so we would have the t's will all be 0. So we'd have 200 over 50, which is equal to 40. Sorry, not 40, 4, equal to 4. And the units here would be thousands of dollars per person because we have millions of people and billions of dollars. So this would be 4 thousands of dollars, which we might just write that as $4,000 per person. That's after H0. H20, we need to put in 20 for T, which when we do the evaluation, we'll get $213 billion on the numerator divided by 52 million people, which is about 4,000. It's about 4.096, or about $4,096 per person. What does this tell us about the country's economy? It tells us the economy is growing because as the number of years go by, there is more money per person. The economy is growing. This is the graph of f of x equals x squared minus x minus 6 over x squared minus x minus 2. And this graph shows us how there are many different features that can show up in the graph of a rational function. It has zeros similar to just regular polynomial functions. Here's a 0 at minus 2, and here's a 0 at 3. But there's these strange breaks and these dashed lines which aren't a part of the graph itself but are showing us something. So these dashed lines that go up and down, there's 2 of them in this case, they're called vertical asymptotes. Okay, and vertical meaning up and down. Asymptotes means that the graph approaches these lines, never touches them. So as we get really close to 2, this blue graph goes way, 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 way up off the screen. And then right at 2, the output's undefined because you have a division by 0 because there's a 2 in the denominator. I'm sorry, a 0 in the denominator when x is 2. And then right after 2, the graph comes really, 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 really close to that dashed line and then jumps back up here. This graph of this rational function also has a horizontal asymptote. And not all rational functions have a horizontal asymptote, but many do. So a horizontal asymptote is a horizontal line that as x gets really, really big or really, really small, it approaches that line, but never, again, never touches it. Now, never touches it means that it never gets exactly to 1 as it's going to infinity and getting really big, but close to x being 0, it might go across that. For instance, we might have, let's do an example here. There might be a graph of a rational function that has a horizontal asymptote, and the graph does something like this, where it jumps over it and then approaches it from above. You might have such a graph like this. So it can actually touch the dotted line. It's just not as it gets really far away from x is 0. Really far away, it just approaches that line. So this is really the long run behavior. And we'll talk more about long run behavior of rational functions in the next section, 13.2. There's one other feature that can happen, which is not in this graph, but we'll show you one later. So this graph doesn't have one, but you could have a thing called a hole, which is a place where the output is undefined, but there's no asymptotic behavior. There's no approaching a line. So now let's look at this same function and find the zeros algebraically. And just to note, throughout the slides I've been spelling zeros wrong. I realized this today. So zeros with an E is a verb, meaning he zeros the scale. So if you have a scale that you can zero, it's a verb. And as a noun, you don't use this E. Okay, so when it's a noun, it should just be zeros. So find the zeros algebraically. So we're trying to find the zeros of this function. It's the same function as we graphed here. So we already know the answer from the graph, -2 and 3, but we need to find it algebraically. So let's factor the denominator. In fact, why don't we factor both the numerator and the denominator of this rational function? So in the numerator we have a 6, -6, and a -1. So that would be -3 and 2. Those multiply to -6 and add to -1. The denominator we have -2 and -1, so that would be -2 and +1. That multiplies to -2 and adds to -1. So here's the factored form of this rational function. And so the zeros would be the places the numerator is 0, which would be +3 and -2. Again, we have to flip the sign of the middle there. So we go back and we see, sure enough, -2 and +3, those are the zeros of this function. Now what about the zeros of the denominator? What are they telling us? So if we see the zeros of the denominator, that tells us the vertical asymptotes are at 2 and -1. So if you come back and look here, you see a vertical asymptote at 2 and a vertical asymptote at -1. The zeros of the denominator will tell us either asymptotic behavior or they will tell us holes. So we'll get into holes in a few minutes. In this case, it's asymptotic behavior. Okay, and I just jumped the gun. So here it says show the domain is all values of x except for -1 and 2. Well, we did that here because the asymptotes at 2 and -1 are where it's divided by 0. So, holes. When both the numerator and denominator have a 0 at the same x value, the graph may have a hole at that x value instead of a vertical asymptote. So going back here, suppose we actually had x plus 1 up here instead of x plus 2. And if that's what we had, then we would have a hole when x is -1 instead of an asymptote. Because essentially these two factors will cancel. It gets rid of a value of our domain. You're not allowed to put in a -1. But otherwise it doesn't change the shape of the graph of x minus 3 over x minus 2. So if both the zeros are simple, there's always a hole. So if you have the situation on the numerator, you have x plus 1, and in the denominator you also have a factor of x plus 1, then you have a hole at x is -1. Okay? Because these will cancel and we'll have what's left over. These are simple zeros. If one or both of the zeros is not simple, it gets complicated. There will only be a hole if the number of zeros in the numerator is greater than or equal to the number of zeros in the denominator. So here, if this were x plus 1 squared over x plus 1, then we still have a hole, okay, at this x value. If it's x to the 10th, we still have a hole. If it's x to the 10th over x to the 9th, we still have a hole. 10 is bigger than 9. If it's x to the 10th over x to the 10th, we still have a hole. That's a 10. We still have a hole because they're the same. They're 10. But if we have x plus 1 over x plus 1 squared, we don't have a hole. We have a vertical asymptote. So if there are more zeros at the same x value in the denominator, here we have a squared, then there will be a vertical asymptote and not a hole. And this is because when you cross off the common factors, you still have sort of the undefined factor in the denominator, which is what's driving this asymptotic behavior in the graph. In other words, as your values of what's left over after canceling get close to that x value, you're going to have really, really big or really, really small numbers because you're getting close to a division by 0. You're dividing by a really small number, which makes a really big number. So how do we find where a hole is? So let's make a concrete example here. Suppose this was x plus 3 over x plus 2, x plus 3 times x plus 1 over x plus 2 times x plus 1. We have a hole at -1 because those are both simple, so there's nothing to worry about with the hole. That's at x of minus 1. So what about the y value? Okay, so the coordinates of a hole are the x value. So that's whatever this is going to be, the opposite of 1, negative 1. And then f prime of x, or f prime of x is the original function f of x with the common factors canceled. So if we cancel the x plus 1, the f prime of x would be x plus 3 over x plus 2. So our graph is going to look like the graph of f prime of x, except there'll be a hole at negative 1. That's the x value. At the y value will be plug in negative 1 for x. So we'd have negative 1 plus 3 over negative 1 plus 2. Negative 1 plus 3 is 2. Negative 1 plus 2 is 1. So we'd have a y value of 2. So the hole would be at negative 1, 2. In other words, to find the coordinates of a hole, we must cancel out the common factors, put in the x value, negative 1, of the original common 0 being negative 1 here. And then the output value, or the y value, will be the y coordinate of the hole, 2. That's how you find the coordinates of a hole in a graph. So let's do an example here with a graph. So here's the graph of x minus 3 over x plus 2. So we see there's a 0 at 3, which isn't labeled, but that's where the 0 is. And then there's a vertical asymptote at negative 2. There's also a horizontal asymptote at 1 here. There's no hole. We just have different zeros in the numerator and the denominator. So the hole only arises if we have the same 0. So here's the graph of a similar function, x minus 3 times x plus 1 over x plus 2 times x plus 1. And here we have a hole. Okay, and the x value is negative 1, the negative of 1. The y value, if we plug in negative 1 after canceling the common factors, we'd have negative 1 minus 3 is minus 4. Negative 1 plus 2 is 1, or negative 4. So the y value would be negative 4. And if you look at the graph, that makes sense. It's right around negative 4 where we have this hole appearing in the graph. So whenever we graph and we have a hole, we put this open circle and don't have the line of the graph going through it. That represents that there's a missing value here in the graph. We're missing the value at negative 1, x of negative 1, because of this domain issue. It's not in the domain. So the domain is x is not equal to 1, minus 1 of this function. Actually, the domain is also x is not equal to minus 1, x is not equal to minus 2, because of the vertical asymptote. So because both those division by zeros are in the denominator, that's the domain of this rational function. Now, while we're on the topic of domain, the range won't include the horizontal asymptote because you never get out a value of 1. So the range would be f of x is never equal to 1. Now, there's never an output of 1. Otherwise, it's all other real numbers. And so what about the case where we have, so if we had more zeros here, it would change the shape of the graph in the denominator, sorry, in the numerator. So if we had, suppose we had x plus 1 squared, there would still be a hole at negative 1. The shape of this graph would change, and the hole's position would change, because we would have, when we cancel the common factors, we would, so here's how you can tell that. If you cancel the common factors in this case, you'd have x minus 3, and you'd still have 1x plus 1 left, because there's 2 of them in the numerator, and only 1 in the denominator. Okay, so you'd have the graph of this rational function with a hole, not this x, not x minus 3 over x plus 2. You still have one of these x plus 1s in the numerator. And so the hole's y value will change, because when we put in negative 1, we're going to get 0 as the y value. So this is always true. When you have a hole, so when you have a hole where the numerator has more zeros at that x value than the denominator, then the y value will be 0 of the hole, which knocks out one of the zeros of the function. So if I ask you what are the zeros of this function, you wouldn't write -1 because it's not in the domain. Remember, it's a division by 0. But the coordinates of the hole, remember the hole is not a part of the graph. It's just where the graph, the piece of the graph is missing would be -1, 0. So this graph would change shape by adding in an extra squared. But there's still a hole at that x value. Now if we add in an extra x plus 1 squared in the denominator, that's what's going to happen next. See the graph change shape again. But now we don't have a hole. We have another vertical asymptote. So, and that's because when we cancel the common factors, the x plus 1 in the denominator to get the f prime, you'd have x plus 2 over x plus 1. So you still have this x plus 1 in the denominator of the canceled f prime of x. So there's still a vertical asymptote at -1. So you have two vertical asymptotes here. You might wonder what happened to the graph inside of -2 and 1. There's actually a little piece of the graph in here that goes way up and way back down and way back up. That is so far above 10 it doesn't show up on this graph. So there is some graph in between here. It's just the really big values of f of x. The output gets really big. So again, just to sum up, if we have balanced number of zeros in the numerator and denominator at a particular x value, we get a hole. And the hole is not going to be at 0 in that case. It'll be somewhere along the shape of the graph. If we have more zeros in the numerator than the denominator at a particular x value, we'll get a hole at 0, where the y value is at 0. And if we have more in the denominator, we'll get just another vertical asymptote at that x value. So that's one of the most complicated parts of rational functions. Let's do some more examples with algebra. Cancel common factors in each of the following rational expressions. Is the resulting expression equivalent to the first one? So let's see, we need to factor the numerator here. So we would have what multiplies to 1 and adds to -2. That would be -1 and -1. Those add to -2 and multiply to 1, which is a perfect square, over x minus 1. These are all x minus 1s. If we cancel the common factor, we would be left with x minus 1, which is not equivalent. Okay? It's not equivalent because the expression x minus 1 is defined when x is 1, but it's undefined here where we divide by it. Not equivalent at x equals 1 specifically is where they're not the same. B, 2x squared plus 4x over 2x plus 6. Well, we can pull an x out of in the numerator. So we have 2x plus 4 over x over 2x plus 6. And we still have a 2 here we can factor out in both the numerator and the denominator. So we can take that 2 out. So we have 2x times x plus 2, moving this x over and pulling the 2 out. 2x times x plus 2 over, and we can pull a 2 out of the denominator, 2x plus 3. And then we can cancel the 2's, which that's never 0. And so we're left with x times x plus 2 over x plus 3. And this is equivalent. And it's equivalent because we didn't do anything that makes it not equivalent. We just canceled 2's and used the distributive law. C, x to the 4th minus 1. We could think of that as a difference of squares, because you would have x squared squared. So x squared squared is x squared squared. Minus 1 would be a difference of squares of x squared and 1. So we can factor it like this. And x squared is either 0 or it's positive. And when we add 1 to it, we'll get something always positive and never 0. So we can cancel that x squared plus 1 that's common in the numerator and the denominator, and we will not change the equivalence. It's equivalent because x squared plus 1 is never equal to 0. Or you can write it's always greater than 0, which tells us it's never equal to 0. In summary, the zeros of the numerator that are distinct, that's really a parenthesis, from the zeros of the denominator are the zeros of the rational function. So we don't get a 0 when we have a whole, but otherwise we have a 0. So that's what tells us the zeros of the overall rational function is the zeros of the numerator. The zeros of the denominator that are distinct from the numerator's zeros are vertical asymptotes of the rational function. So in general, the denominator zeros tells the vertical asymptotes. Now we have the special case of the whole. If the numerator and denominator share a 0, there may be a whole. Remember, if the number of zeros at the x value is greater than or equal to the number in the denominator. Or we might have the vertical asymptote case when it's not a whole. So when you have the same zeros in the numerator and the denominator, either you'll have a whole or a vertical asymptote based on the number of zeros that you have in each. To find the coordinates of the whole, cancel out the common factors first, and then find the y value for the x value of the whole after canceling. And if you forget this rule above, if you did this, you'd end up with a division by 0 because you'd have an extra 0 in the denominator, which would again tell you there's actually an asymptote there, not a whole. And we'll discuss the long run behavior in the next section.